Right now, firefighters are battling devastating wildfires in Spokane, Washington. And state officials there are saying the flames have already destroyed about 700 buildings, threatening around 10,000 more.
NASA satellites detected something scientists couldn't immediately explain. At first, it looked like an ordinary wildfire. Then, the thermal data changed. Hour after hour, the fire wasn't simply spreading. It was accelerating. Only later would firefighters realize they were losing control. By then, one of Washington's largest cities was surrounded by flames. More than 62,000 people were evacuating, and over 640 structures would ultimately be destroyed. Today on DiscoverTube, we uncover what the satellites saw long before the full disaster unfolded. NASA detected something unusual before Washington's fire exploded. NASA satellites first noticed the fire long before most people understood what was unfolding below. At first, there was nothing particularly remarkable about it. During every wildfire season, satellites detect hundreds of thermal hotspots across the western United States. Most remain relatively small, and many are contained before they ever threaten nearby communities. This one looked no different. Then, the data changed. Instead of expanding gradually, the thermal signature began growing at a rate scientists rarely expect during the earlier stages of a wildfire. Every new satellite pass revealed a larger area of intense heat, while weather models suggested conditions were becoming increasingly favorable for rapid fire growth. Researchers immediately began asking the same question: why was this fire accelerating so quickly? The answer wouldn't come from the flames themselves. It would come from space. Today on DiscoverTube, we follow the scientific investigation that revealed why this wildfire evolved into one of the most destructive urban fires in Washington's recent history, and how satellites helped scientists understand the disaster while it was still unfolding. The first warning came from orbit. Wildfires usually begin with a phone call. Someone reports smoke. A passing driver notices flames. Firefighters are dispatched to investigate. Scientists, however, often receive a completely different kind of warning. Orbiting hundreds of miles above Earth are satellites constantly monitoring the planet's surface. Some observe cloud development. Others measure vegetation health, atmospheric moisture, or land temperatures. Among the most important wildfire monitoring systems is NASA's Fire Information for Resource Management System, better known as FIRMS. Rather than looking for visible flames, FIRMS detects infrared radiation emitted by unusually hot surfaces. Sophisticated algorithms compare millions of temperature measurements, allowing scientists to identify active fires, even when thick smoke hides them from view. When Washington's first hotspot appeared, the system worked exactly as designed. But as additional observations arrived, researchers noticed something unexpected. The hotspot wasn't simply getting larger, it was accelerating. That immediately raised concerns. Large wildfires don't happen because flames are hot. They happen because several independent environmental systems begin working together. To understand what was happening, scientists needed far more than satellite imagery. They needed evidence. The data told a bigger story. One satellite can show where a fire is burning. It cannot explain why. To answer that question, researchers combined information from multiple agencies. NASA tracked thermal activity. NOAA analyzed weather conditions. Ground stations measured humidity. Forecasters examined wind patterns. Vegetation specialists monitored fuel moisture. Individually, none of these observations seemed extraordinary. Together, they revealed a landscape that had quietly become extremely vulnerable. Weeks of hot, dry weather had steadily removed moisture from grasses, shrubs, and small vegetation. Scientists refer to these materials as fine fuels because they ignite much more easily than larger trees. At the same time, relative humidity remained unusually low. Temperatures stayed well above seasonal averages. Forecast models indicated strengthening winds moving across central Washington. None of these factors guaranteed a major wildfire, but together they dramatically increased the probability that even a relatively small ignition could escape containment. Researchers weren't simply watching a fire. They were watching weeks of environmental conditions finally reach a tipping point.
Scientists already knew what they were looking for. Modern wildfire research has fundamentally changed over the last 2 decades. In the past, scientists often investigated fires after they ended. Today, they study them while they happen. Every satellite image is compared with previous observations. Every weather update is fed into computer models. Every new hotspot is analysed alongside wind forecasts, terrain, vegetation, and historical fire behaviour. The goal isn't simply documenting a disaster, it's understanding where the fire may move next. As Washington's wildfire continued expanding, scientists noticed another pattern beginning to emerge. The fire wasn't spreading evenly. Certain areas suddenly experienced explosive growth. Others remained relatively stable. That suggested another force was driving the disaster. It wasn't temperature. It wasn't drought. It wasn't the terrain alone. The atmosphere itself had begun influencing how the fire behaved. Meteorologists already suspected what they would find, but the next round of satellite observations confirmed it. The wind wasn't simply pushing the flames. It was transforming the entire wildfire into something far more dangerous. Scientists realized this was no longer a normal wildfire. At first, researchers believed drought explained the fire's rapid growth. Then, the atmosphere began telling a different story. As new observations arrived from NOAA weather stations and GOES weather satellites, meteorologists noticed winds strengthening across central Washington. On paper, the increase didn't appear extraordinary. But wildfire scientists know wind isn't measured by speed alone. It's measured by what it does to a fire. A 10-mile-per-hour increase can completely transform fire behavior if vegetation is already critically dry. Flames lean closer to unburned fuels, transferring heat more efficiently. Fresh oxygen feeds combustion, allowing temperatures to rise even further. Yet researchers believed another process posed an even greater danger, one that satellites couldn't directly see. The fire was starting new fires. Most people imagine a wildfire moving like a wave, one wall of flames advancing across the landscape. Modern fire research shows that's often not how destructive wildfires spread. Instead, powerful winds tear burning bark, branches, pine needles, and other debris away from the main fire. These glowing embers can remain hot while traveling hundreds of meters through the air, sometimes even farther. When they land in dry grass, wooden fences, rooftop gutters, or shrubs surrounding homes, they ignite entirely new fires. Fire scientists call this spotting, and spotting changes everything. Instead of stopping one advancing firefront, firefighters suddenly face dozens of independent ignitions occurring simultaneously. Researchers have found that during many of North America's most destructive wildfires, embers, not direct flames, were responsible for destroying large numbers of homes. That explains one of the strangest scenes seen after major fires. One house survives almost untouched. The neighboring house is completely destroyed. The difference often comes down to where a single ember landed. Satellites confirmed the fire was outrunning firefighters. As the fire intensified, NASA's firms continued identifying new thermal hotspots, while NOAA's GO satellites tracked the expanding smoke plume overhead. Emergency managers compared every satellite update with reports arriving from crews on the ground. A pattern quickly emerged. The fire perimeter wasn't simply growing outward. New hotspots were appearing well ahead of the main flames. That matched exactly what fire behavior specialists expected from a wind-driven spotting event. For firefighters, this created an enormous challenge. Roads considered safe only minutes earlier could suddenly become threatened. Containment lines built to stop one firefront became far less effective when entirely new fires appeared beyond them. Researchers weren't simply documenting a fast-moving wildfire anymore. They were watching multiple fires develop at the same time. The city was becoming part of the fire. Until now, vegetation had provided most of the fuel. That was beginning to change. As the fire approached developed areas, scientists knew the dynamics would become far more complicated. Forests burn differently than neighborhoods. Inside cities, homes, garages, vehicles, wooden fences, decks, utility poles, and landscaping all become potential fuel sources. Every burning structure releases additional heat. Every collapsing roof produces more embers. Every new ignition increases the fire's intensity. Fire behavior specialists describe this transition as an urban interface wildfire, where the boundary between natural vegetation and human development disappears. Once that happens, predicting fire spread becomes significantly more difficult. The landscape is no longer the only factor. The city itself begins influencing how the fire behaves. Scientists were watching a dangerous feedback loop. As more structures ignited, researchers observed another important process. Every new fire generated additional heat. That heat strengthened rising air currents above the fire. Stronger convection pulled in more oxygen. More oxygen intensified combustion. The cycle repeated. Wildfire scientists call this a positive feedback loop. It doesn't happen during every fire, but under the right combination of dry fuels, strong winds, and expanding ignition sources, fire intensity can increase much faster than traditional models predict. This was one of those moments. The disaster was no longer being driven by weather alone. The fire itself was beginning to influence the environment around it. And that led scientists to an even more remarkable discovery. The smoke column rising above Washington wasn't just carrying ash into the sky. It was beginning to change the atmosphere itself. The fire started changing the atmosphere. Until this point, scientists believed the atmosphere was controlling the fire. New satellite data suggested something far more remarkable. The fire was beginning to influence the atmosphere in return. That marked one of the most dangerous phases of the disaster. The smoke was rising higher than expected. NOAA's GOES weather satellites continuously monitored the smoke plume as it expanded across eastern Washington. Every few minutes, fresh imagery revealed another change. The column wasn't simply drifting with the wind. It was rising rapidly into the upper atmosphere. For meteorologists, that immediately signaled intense convection. A wildfire acts like a giant heat engine. As vegetation, buildings, and vehicles burn, enormous amounts of hot air rise upward. Cooler air rushes in below to replace it, feeding the flames with fresh oxygen. The stronger the fire becomes, the stronger this circulation can become. Researchers have observed this process during many of North America's largest wildfires. But in extreme cases, something even more unusual happens. The fire begins creating its own weather. Scientists were watching a fire-generated weather system. As the smoke continued climbing thousands of feet into the atmosphere, researchers searched for signs of pyrocumulus development. These towering clouds form differently from ordinary weather clouds. Instead of being driven mainly by sunlight warming Earth's surface, they're powered by the tremendous heat released by the fire itself. As hot air rises, it cools. Moisture begins condensing inside the smoke. A cloud starts to form. Although not every wildfire develops a fully mature pyrocumulus cloud, even large convection columns can dramatically influence local weather. They can strengthen wind shifts, reduce visibility for firefighting aircraft, and in the most extreme situations, even generate lightning, capable of starting entirely new fires. Scientists continue studying these events because they remain one of the least predictable aspects of wildfire behavior. This Washington fire offered another valuable opportunity to understand how large fires interact with the atmosphere above them. The smoke became a second emergency. While firefighters focused on containing the flames, public health experts focused on the sky. Wildfire smoke contains thousands of microscopic particles released as vegetation, buildings, plastics, and other materials burn. One of the greatest concerns is PM 2.5, particles so small they can travel deep into the lungs and in some cases enter the bloodstream. Unlike flames, smoke doesn't stop at evacuation zones. Changing winds can carry it across entire states. Using satellite observations together with atmospheric transport models, NOAA tracked where the smoke plume was moving and which communities were likely to experience deteriorating air quality. Health officials used those forecasts to issue advisories for vulnerable groups, including children, older adults, and people with respiratory or cardiovascular conditions. For many residents living far from the fire, the smoke became the greatest immediate threat.
Artificial intelligence was quietly supporting the response.
Most people imagine wildfire response as helicopters, bulldozers, and firefighters working on the front lines. Behind the scenes, another battle was taking place, inside emergency operations centers. Modern wildfire management increasingly relies on artificial intelligence to process enormous amounts of information arriving every minute. Satellite imagery, weather forecasts, terrain models, fuel moisture, wind projections, historical wildfire behavior. No human team could analyze all of this data fast enough. Machine learning systems help identify patterns, estimate possible fire spread, and highlight areas where conditions are changing most rapidly. The decisions still belong to experienced fire managers, but AI helps them understand the situation much faster than ever before. This disaster demonstrated how technology has fundamentally changed wildfire response, not by replacing firefighters, but by giving them better information. The flames eventually slowed. The investigation didn't. As weather conditions gradually improved and containment increased, public attention slowly shifted elsewhere. For scientists, however, the most important work was only beginning. Once active flames disappear, researchers gain access to something impossible to study during the emergency: the complete burn scar. From space, burned landscapes appear as enormous dark patterns stretching across forests, grasslands, and neighborhoods. By comparing satellite images taken before and after the wildfire, scientists can map exactly where the fire burned, how severely vegetation was damaged, and which areas may now face new environmental risks. The flames had finally begun disappearing, but the landscape was about to reveal an entirely new chapter of the story. What scientists learned from Washington's largest urban wildfire. Eventually, the flames began slowing, containment increased, evacuation zones were gradually reduced. For thousands of residents, the disaster was finally coming to an end. For scientists, it was only entering its most important phase. Modern wildfires don't end when the last flames disappear. They leave behind millions of measurements, satellite images, weather observations, and field reports that researchers will analyze for years. Every dataset helps answer one critical question: how can the next disaster be predicted sooner and become less destructive? The burn scar revealed the fire's hidden story. Within days, researchers from NASA, the US Geological Survey, the US Forest Service, and other agencies began comparing satellite images taken before and after the fire. The differences told a story that couldn't be seen from the ground. Scientists mapped exactly where vegetation had burned. They identified neighborhoods that experienced the highest fire intensity. They analyzed which forests suffered the greatest damage and which areas remained surprisingly untouched. These burn scar maps are far more than images. They become the foundation for future research. Engineers use them to evaluate infrastructure damage. Ecologists study how forests recover. Hydrologists identify slopes vulnerable to flooding and landslides. Emergency managers improve evacuation planning. Every major wildfire becomes another natural experiment. The next hazard often begins after the fire. One of the biggest public misconceptions is that the danger ends once the flames are extinguished. Researchers know that's rarely true. Healthy vegetation normally stabilizes hillsides, slows rainfall, and helps soil absorb water. After an intense wildfire, many of those natural defenses disappear. When heavy rain eventually returns, burned landscapes can produce flash floods, landslides, and fast-moving debris flows carrying mud, rocks, and fallen trees. Scientists therefore continue monitoring major burn scars long after the smoke has cleared. Recovery isn't measured in days, sometimes it takes decades.
Why researchers believe fires like this could become more common. No single factor caused this disaster. Instead, scientists identified several conditions occurring at the same time. Critically dry vegetation, low humidity, strengthening winds, and a growing number of homes built where forests and cities meet. Researchers call these regions the wildland-urban interface. Across the western United States, millions of people now live in these transition zones. That doesn't necessarily mean wildfires are becoming more frequent everywhere, but it does mean more communities are exposed when they occur. This is why agencies such as the US Forest Service, NOAA, and state fire authorities continue investing in prescribed burns, vegetation management, improved building standards, and increasingly sophisticated forecasting systems. The goal isn't to eliminate wildfires. That's impossible. Wildfire is a natural part of many Western ecosystems. The goal is to prevent natural fires from becoming urban disasters. A new era of wildfire science. 20 years ago, scientists often reconstructed wildfires after they ended. Today, they investigate them while they're happening. Satellites identify hotspots within minutes. Weather models predict changing wind conditions. Artificial intelligence analyzes millions of incoming data points. Firefighters receive updated maps throughout the day. Emergency managers adjust evacuations using near real-time information. For the first time in history, researchers can watch an entire natural disaster unfold from space while simultaneously comparing observations from aircraft, weather stations, drones, and crews on the ground. No technology can stop a wildfire, but technology can provide something just as valuable: time. Sometimes only a few extra minutes, sometimes several hours. Those moments can make the difference between protecting a neighborhood or losing it. This wildfire forced more than 62,000 people to evacuate and destroyed over 640 structures, making it one of Washington's most destructive urban wildfire events in recent years. But beyond the destruction, it also revealed something remarkable. Modern science no longer waits for disasters to end before learning from them. NASA satellites tracked the fire from orbit. NOAA monitored the changing atmosphere. Researchers combined thermal imagery, weather models, and field observations to understand why the fire accelerated, how it spread, and what lessons could help protect future communities. Every wildfire leaves behind ashes, but it also leaves behind knowledge. Knowledge that improves forecasts, strengthens emergency planning, and helps scientists better understand one of nature's most complex and unpredictable forces. Here on DiscoverTube, we believe the world's greatest discoveries aren't always made in laboratories. Sometimes they're made while history is still unfolding. If you enjoyed this documentary, subscribe to DiscoverTube for more in-depth investigations into Earth's most fascinating natural events, where science explains the stories making headlines around the world. And now we'd like to hear from you. What surprised you most about this investigation? Was it how NASA detected the fire from space? How embers,
not flames, destroyed entire neighborhoods. Or how scientists continue learning from the disaster long after the smoke has disappeared. Let us know in the comments below, because every major disaster teaches us something new about the planet we call home.